Humanity has entered what energy experts call the age of electricity. Every second, cities light up, factories operate, data centers process information, and billions of people rely on electricity for almost every aspect of modern life. In 2024 alone, the world consumed more than 30,000 terawatt-hours of electricity, an almost unimaginable amount of energy. And demand is still growing, which raises a fascinating question. Could nuclear energy power the entire world? Today, nuclear power already plays a major role in the global energy system. Across dozens of countries, hundreds of reactors operate day and night. Unlike solar panels, they do not depend on sunlight. Unlike wind turbines, they do not depend on weather. They generate electricity continuously, often for months at a time. In 2024, nuclear reactors produced approximately 2,667 terawatt-hours of electricity. That was enough to supply about 9% of the world's electricity demand. 9% from just one technology. But what if we push that idea further? What if nuclear power supplied not 9%, but all of it? To answer that question, we first need to understand scale. A modern nuclear reactor producing 1 gigawatt of electricity can generate roughly 7.3 terawatt-hours per year. That is enough electricity for millions of people. But the world is enormous. Humanity consumed more than 30,000 terawatt-hours of electricity in 2024. So how many reactors would be required? The answer is surprisingly simple. 30,000 divided by 7.3. Approximately 4,100 reactors. That sounds like a lot, because it is. Today, the world operates roughly 440 reactors, meaning a fully nuclear electricity system would require a fleet nearly 10 times larger than today's. At first glance, that number sounds impossible. 4,000 reactors. But physics tells a different story. The Earth contains enough uranium to support significant growth in nuclear energy. According to assessments by the IAEA and OECD Nuclear Energy Agency, known uranium resources are sufficient to support continued expansion of nuclear power. But the story does not end there. Future reactor technologies could extract far more energy from nuclear fuel than today's reactors, potentially extending fuel resources far beyond current expectations. The greatest obstacle is not uranium, and it is not reactor technology. It is scale. Building a nuclear power plant requires steel, concrete, specialized equipment, and highly trained workers. Now imagine doing that thousands of times, across continents, across decades, across entire industrial supply chains. The challenge is not physics. The challenge is civilization itself. The numbers reveal something surprising. Nuclear energy is not limited by a lack of power. The reactors already exist. The physics already works. The real question is not whether it can be done. The real question is how quickly it could be done, and whether societies are willing to make that investment. Can nuclear energy power the entire world's electricity demand? According to the available evidence, it appears possible. Not because nuclear energy is magical, not because the challenge is easy, but because the laws of physics do not stand in the way. The greatest barriers are human decisions, industrial capacity, and time. And perhaps, That is the most interesting answer of all. This is Reactor Atlas. One reactor. One truth. At a time.